Hello, Namaste. Myself Ankitha Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ART.SKILL.PASSION. Chapter 13 Nuclei 13.1 Introduction. In the previous chapter, we have learned that in every atom, the positive charge and mass are densely concentrated at the center of the atom, forming its nucleus. The overall dimensions of a nucleus are much smaller than those of an atom. Experiments on scattering of alpha particles demonstrated that the radius of a nucleus was smaller than the radius of an atom by a factor of about 10 to the power 4. This means the volume of a nucleus is about 10 to the power minus 12 times the volume of the atom. In other words, an atom is almost empty. If an atom is enlarged to the size of a classroom, the nucleus would be of the size of pinhead. Nevertheless, the nucleus contains more than 99.9% of the mass of an atom. Does the nucleus have a structure just as the atom does? If so, what are the constituents of the nucleus? How are these held together? In this chapter, we shall look for answers to such questions. We shall discuss various properties of nuclei such as their size, mass, and stability, and also associated nuclear phenomena such as radioactivity, fission, and fusion. 13.2 Atomic masses and composition of nucleus. The mass of an atom is very small compared to a kilogram. For example, the mass of a carbon atom C12 is 1.992647 into 10 to the power minus 26 kg. Kilogram is not a very convenient unit to measure such small quantities. Therefore, a different mass unit is used for expressing atomic masses. This unit is the atomic mass unit U, defined as 1/12 of the mass of the carbon C12 atom. According to this definition, 1 U is equal to mass of 1 C12 atom by 12 is equal to 1.992647 into 10 to the power minus 26 kg by 12 is equal to 1.66053 into 10 to the power minus 27 kg. The atomic masses of various elements expressed in atomic mass unit U are close to being integral multiple of the mass of a hydrogen atom. There are, however, many striking exceptions to this rule. For example, the atomic mass of chlorine atom is 35.46 U. Accurate measurement of atomic masses is carried out with a mass spectrometer. This measurement of atomic masses reveals the existence of different types of atoms of the same element, which exhibit the same chemical properties but differ in mass. Such atomic species of the same element differing in mass are called isotopes. In Greek, isotopes means the same place, that is, they occur in the same place in the periodic table of elements. It was found that practically every element consists of a mixture of several isotopes. The relative abundance of different isotopes differ from element to element. Chlorine,
for example, has two isotopes having masses 34.98 U and 36.98 U, which are nearly integral multiples of the mass of a hydrogen atom. The relative abundance of these isotopes are 75.4 and 24.6% respectively. Thus, the average mass of a chlorine atom is obtained by the weighted average of the mass of the two isotopes, which works out to be is equal to 75.4 into 34.98 plus 24.6 into 36.98 divided by 100 is equal to 35.47 U, which agrees with the atomic mass of chlorine. Even the lightest element, hydrogen, has three isotopes having masses 1.0078 U and 2.0141 U and 3.0160 U. The nucleus of the lightest atom of the hydrogen, which has a relative abundance of 99.985%, is called the proton. The mass of a proton is Mp is equal to 1.00727 U is equal to 1.67262 into 10 to the power minus 27 kg. This is equal to the mass of the hydrogen atom is equals to 1.00783 U minus the mass of a single electron Me is equal to 0.00055 U. The other two isotopes of hydrogen are called deuterium and tritium. Tritium nuclei, being unstable, do not occur naturally and are produced artificially in the laboratories. The positive charge in the nucleus is that of the protons. A proton carries 1 unit of fundamental charge and is stable. It was earlier thought that the nucleus may contain electrons, but this was ruled out later using arguments based on quantum theory. All the electrons of an atom are outside the nucleus. We know that the number of these electrons outside the nucleus of the atom is Z, the atomic number. The total charge of the atomic electrons is thus minus Ze, and since the atom is neutral, the charge of the nuclei is plus Ze. The number of protons in the nucleus of the atom is therefore exactly Z, the atomic number. Discovery of neutron. Since the nuclei of deuterium and tritium are isotopes of hydrogen, they must contain only one proton each. But the masses of the nuclei of hydrogen, deuterium and tritium are in the ratios of 1:2:3. Therefore, the nuclei of deuterium and tritium must contain, in addition to a proton, some neutral matter. The amount of neutral matter present in the nuclei of these isotopes, expressed in units of mass of a proton, is approximately equal to 1 and 2 respectively. This fact indicates that the nuclei of atoms contain, in addition to protons, neutral matter in multiples of a basic unit. This hypothesis was verified in 1932 by James Chadwick, who observed emission of neutral radiation when beryllium nuclei were bombarded with alpha particles. Alpha particles are helium nuclei, to be discussed in later section. It was found that this neutral radiation could knock out protons from light nuclei such as those of helium, carbon and nitrogen. The only neutral radiation known at that time was protons, electromagnetic radiation. Applications of the principle of conservation of energy and momentum showed that if the neutral radiation consisted of protons, the energy of photons would have to be much higher than is available from bombardment of beryllium nuclei with alpha particles. The clue to this puzzle, which Chadwick satisfactorily solved, was to assume that the neutral radiation consists of a new type of neutral particles called neutrons. From conservation of energy and momentum, he was able to determine the mass of new particles as very nearly the same as mass of proton. The mass of neutron is now known to a higher degree of accuracy. It is Mn is equal to 1.00866 U is equal to 1.6749 into 10 to the power minus 27 kg. Chadwick was awarded the 1935 Nobel Prize in Physics for his discovery of the neutron. A free neutron, unlike a free proton, is unstable. It decays into a photon and electron and a antineutrino, another elementary particle, and has a mean life of about 1000 seconds. It is, however, stable inside the nucleus. The composition of a nucleus can now be described using the following terms and symbol. Z, atomic number is equal to number of protons. N, neutron number is equal to number of neutrons. A, mass number is equal to Z plus N is equal to total number of protons and neutrons. One also uses the term nucleon for a proton or a neutron. Thus, the number of nucleons in an atom is its mass number A. Nuclear species of nucleus are shown by the notation XAZ, where X is the chemical symbol of the species. For example, the nucleus of the gold is denoted by AU 19779. It contains 197 nucleons, of which 79 are protons and the result 118 are neutrons. The composition of isotopes of an element can now be readily explained. The nuclei of isotopes of a given element contain the same number of protons but differ from each other in their number of neutrons. Deuterium 1H2, which is an isotope of hydrogen, contains 1 proton and 1 neutron. S, isotope tritium 1H3, contains 1 proton and A is equal to 204. We have already mentioned that chemical properties of elements depend on their electronic structure. As the atoms of isotopes have identical electronic structure, they have identical chemical behavior and are placed in the same location in the periodic table. All nucleids with the same mass number A are called isobars. For example, the nucleids 1H3 and 2He3 are isobars. Nucleids with same neutron number N but different atomic number Z, for example 80Hg198 and 79Au197, are called isotones. 13.3 Size of the nucleus. As we have seen in Chapter 12, Rutherford was the pioneer who postulated and established the existence of the atomic nucleus. At Rutherford's suggestion, Geiger and Marsden performed their classic experiment on the scattering of alpha particles from thin gold foil. Their experiment revealed that the distance of closest approach to a gold nucleus of an alpha particles of kinetic energy 5.5 MeV is about 4.0 into 10 to the power minus 14 m. The scattering of alpha particle by the gold sheet could be understood by Rutherford by assuming that the Coulomb repulsive force was solely responsible for scattering. Since the positive charge is confined to the nucleus, the actual size of the nucleus has to be less than 4.0 into 10 to the power minus 14 m. If we use alpha particles of higher energies than 5.5 MeV, the distance of closest approach to the gold nucleus will be smaller, and at some point the scattering will begin to be affected by the short-range nuclear forces and differ from Rutherford's calculations. Rutherford calculations are based on pure Coulomb repulsion between the positive charges of the alpha particle and the gold nucleus. From the distance at which devastation set in, nuclear sizes can be inferred. By performing scattering experiments in which fast electrons instead of alpha particles are projectiles that bombard targets made up of various elements. The size of nuclei of various elements have been accurately measured. It has been found that a nucleus of mass number A has a radius r is equal to r0 a 1 by 3, where r0 is equal to 1.2 into 10 to the power minus 15 m is equal to 12.5 fm. 1 fm is equal to 10 to the power minus 15 m. This means the volume of the nucleus, which is proportional to R3, is proportional to A. Thus, the density of nucleus is constant, independent of A. For all nuclei, different nuclei are like a drop of liquid of constant density. The density of nuclear matter is approximately 2.3 into 10 to the power 17 kg meter minus 3. This density is very large compared to the ordinary matter, say water, which is 10 to the power 3 kg meter to the power of minus 3. This is understandable, as we have already seen that most of the atom is empty. Ordinary matter consisting of atoms has a large amount of empty spaces. 13.4 Mass energy and nuclear binding energy. 13.4.1 Mass energy. Einstein showed from this theory of special relativity that it is necessary to treat mass as another form of energy. Before the advent of this theory of special relativity, it was presumed that mass and energy were conserved separately in a reaction. However, Einstein showed that mass is another form of energy, and one can convert mass to energy into other forms of energy, say kinetic energy and vice versa. Einstein gave the famous mass energy equivalence relation E is equal to mc square. Here the energy equivalent of mass m is related by the above equation, and c is the velocity of light in vacuum and is approximately equal to 3 into 10 to the power 8 meter per second inverse. Experimental verification of the Einstein's mass energy relation has been achieved in the study of nuclear reactions amongst nucleons, nuclei, electrons, and other more recently discovered particles. In a reaction, the conservation law of energy states that the initial energy and the final energy are equal, provided the energy associated with mass is also included. This concept is most important in understanding nuclear masses and the interaction of nuclei with one another. They form the subject matter of the next few sections. 13.4.2 Nuclear binding energy. In section 13.2, we have seen that the nucleus is made up of neutrons and protons. Therefore, it may be expected that the mass of the nucleus is equal to the total mass of its individual protons and neutrons. However, the nuclear mass m is found to be always less than this. For example, let us consider 8O16, a nucleus which has 8 neutrons and 8 protons. We have mass of 8 neutrons is equal to 8 into 1.00866 U. Mass of 8 proton is equal to 8 into 1.00727 U. Mass of 8 electrons is equal to 8 into 0.00055 U. Therefore, the expected mass of 8O16 nucleus is equal to 8 into 2.01593 U is equal to 16.12744 U. The atomic mass of 1608 found from mass spectroscopy experiment is seen to be 15.99493 U. Subtracting the mass of electrons 8 into 0.00055 U, from this we get the experimental mass of 8016 nucleus to be 15.99053 U. Thus, we find the mass of the 8016 nucleus is less than the total mass of its constituency by 0.13691 U. The difference in mass of a nucleus and its constituents delta m is called the mass defect and is given by delta m is equal to ZMP plus A minus Z Mn minus M. What is the meaning of the mass defect? It is here that Einstein equivalence of mass and energy plays a role. Since the mass of the oxygen nucleus is less than the sum of the masses of its constituents, 8 protons and 8 neutrons, in the unbounded state, the equivalent energy of the oxygen nucleus is less than that of some of the equivalent energies of its constituents. If one wants to break the oxygen nucleus into 8 protons and 8 neutrons, this extra energy delta mc squared has to be supplied. This energy required EB is related to the mass defect by EB is equal to delta mc squared. If a certain number of neutrons and protons are brought together to form a nucleus of a certain charge and mass, and energy EB will be released. In this process, the energy EB is called the binding energy of the nucleus. If we separate a nucleus into its nucleons, we would have to supply a total energy equal to EB to those particles, although we cannot tear apart a nucleus in this way. The nuclear binding energy is still a convenient measure of how well a nucleus is held together. A more useful measure of the binding between the constituents of the nucleus is the binding energy per nucleon, EBN, which is the ratio of the binding energy EB of a nucleus to the number of the nucleons A in that nucleus. EBN is equal to EB by A. We can think of binding energy per nucleon as the average energy per nucleon needed to separate a nucleus into its individual nucleons. Figure 13.1 is a plot of the binding energy per nucleon E, B, N versus the mass number A for a large number of nuclei. We notice the following main features of the plot. First, the binding energy per nucleon EBN is practically constant, that is practically independent of the atomic number for nuclei of middle mass number. 30 is lesser than A, it is lesser than 170. The curve has a maximum of about 8.75 MeV for A is equal to 56 and has a value of 7.6 MeV for A is equal to 238. Second, EBN is lower for both light nuclei. A is lesser than 30 and heavy nuclei A is greater than 170. We can draw some conclusion from these two observations. The force is attractive and sufficiently strong to produce a binding energy of a few MeV per nucleon. The constancy of the binding energy in the range 30 is lesser than A and it is lesser than 170 is a consequence of the fact that the nuclear force is short range. Consider a particular nucleon inside a sufficiently large nucleus. It will be under the influence of only some of its neighbors, which come with the range of the nuclear force. If any other nucleon is at the distance more than the range of the nuclear force from the particular nucleon, it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have a maximum of p neighbors within the range of nuclear force, its binding energy would be proportional to p. Let the binding energy of the nucleus be pk, where k is a constant having the dimensions of energy. If we increase A by adding nucleons, they will not change the binding energy of a nucleon inside. Since most of the nucleons in a large nucleus resident inside it and not on the surface, the change in binding energy per nucleon would be small. The binding energy per nucleon is a constant and is approximately equal to pk. The property that a given nucleon influences only nucleons close to it is also referred to as saturation property of the nuclear force. Third, a very heavy nucleus, say A is equal to 240, has lower binding energy per nucleon compared to that of a nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into 2, A is equal to 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the processes. It has very important implication for energy production through fusion, to be discussed in later session 13.7.1. Fourth, consider two very light nuclei. A is lesser than 10 joining to form a heavier nucleus. The binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process of fusion. This is the energy source of sum, to be discussed later in session 13.7.3. 13.5 Nuclear force. The force that determines the motion of atomic electron is the familiar Coulomb force. In session 13.4, we have seen that for average mass nuclei, the binding energy per nucleon is approximately 8 MeV. which is much larger than the binding energy in atoms. Therefore, to bind a nucleus together, there must be a strong attractive force of a totally different kind. It must be strong enough to overcome the repulsion between the positively charged protons and to bind both protons and neutrons into the tiny nuclear volume. We have already seen that the constancy of binding energy per nucleon can be understood in terms of its short range. Many features of the nuclear binding force are summarized below. These are obtained from a variety of experiments carried out during 1930 to 1950. First, the nuclear force is much stronger than the Coulomb force, acting between charges, or the gravitational force between masses. The nuclear binding force has to dominate over the Coulomb's repulsive force between proton inside the nucleus. This happens only because the nuclear force is much stronger than the Coulomb force. The gravitational force is much weaker than even Coulomb force. Second, the nuclear force between two nucleons falls rapidly to zero as the distance is more than a few femtometers. This leads to saturation of force in a medium or a large size nucleus, which is the reason for the constancy of the binding energy per nucleon. A rough plot of the potential energy between two nucleons as a function of distance is shown in the figure 13.2. The potential energy is a minimum at a distance r0 of about 0.8 femtometer. This means the force is attractive for distance larger than 0.8 fm and repulsive if they are separated by distances less than 0.8 fm. Third, the nuclear force between the neutrons, proton-neutron and proton-proton is approximately the same. The nuclear force does not depend on the electric charge. Unlike Coulomb's law or the Newton's law of gravitation, there is no simple mathematical form of the nuclear force. 13.6 Radioactivity. A.H. Beechworth discovered radioactivity in 1896 purely by accident while studying the fluorescence and phosphorescence of compounds irradiated with visible light. Beechworth observed an interesting phenomena after illuminating some pieces of uranium potassium sulfate with visible light. He wrapped them in black paper and separated the package from a photographic plate by a piece of silver. When after several hours of exposure the photographic plate was observed, it showed blackening due to something that must have been emitted by the compound and was able to penetrate both black paper and the silver. Experiments performed subsequently showed that radioactivity was a nuclear phenomenon in which an unstable nucleus undergoes a decay. This is referred to as radioactive decay. Three types of radioactive decay occur in nature. First, alpha decay, in which a helium nucleus 2He4 is emitted. Second, beta decay, in which electrons or positrons particle with the same mass as electrons but with a charge exactly opposite to that of electrons are emitted. Third, gamma decay, in which high energy unders of keV or more photons are emitted. Each of this decay will be considered in subsequent subsections. 13.6.1 Law of Radioactive Decay. In any radioactive sample which undergoes alpha, beta or gamma decay, it is found that the number of nuclei undergoing the decay per unit time is proportional to the total number of nuclei in the sample. If n is the number of nuclei in the sample and delta n undergo decay in time delta t, then delta n by delta t is proportional to n, or delta n by delta t is equal to lambda n, where n is called the radioactive decay constant or disintegration constant. The change in the number of nuclei in the sample is dn is equal to minus delta n in the time delta t. Thus the rate of change of n is in the limit delta t is proportional to 0. dn by dt is equal to minus lambda n, or dn by n is equal to minus lambda dt. Now integrating both sides of the above equations, we get integral n naught dn by n is equal to minus lambda integral t naught dt, or in n is equal to minus 1 n naught is equal to minus lambda into t minus t naught. Here n naught is the number of radioactive nuclei in the sample at some arbitrary time t naught, and n is the number of radioactive nuclei at any subsequent time t. Setting t naught is equal to 0 and rearranging equation 13.12 gives us 1n n by n naught is equal to minus lambda t, which gives n into t is equal to n naught e to the power minus lambda t. Note for the example, the light bulbs follow no such exponential decay law. If we test 1000 bulbs of their life time span before they burn out or fuse, we accept that they will decay. That is, burn out at more or less the same time. The decay of radionuclides follows quite a different law. The law of radioactive decay, represented by equation 13.14. The total decay rate R of a sample is the number of nuclei disintegrating per unit time. Suppose in a time interval dt, the decay count measured is delta n. Then dn is equal to minus delta n. The positive quantity R is then defined as R is equal to minus dn by dt. Differentiating equation 13.14, we get R is equal to lambda n naught e minus lambda t, or R is equal to R naught e minus lambda t. This is equivalent to the law of radioactivity decay, since you can integrate equation 13.15 to get back equation 13.14. Clearly R naught is equal to lambda n naught is the decay rate at t is equal to 0. The decay rate R at a certain time t and the number of undecayed nuclei n at the same time as related by R is equal to lambda n. The decay rate of a sample rather than the number of radioactive nuclei is a more direct experimentally measurable quantity and is given a specific name, activity. The SI unit for activity is big word named after the discoverer of radioactivity, Henry Becquerel. 1 Becquerel is simply equal to 1 disintegration or decay per second. There is also another unit named Curie that is widely used and is related to SI unit as 1 Curie is equal to 1 Ci is equal to 3.7 into 10 to the power 10 decay per second is equal to 3.7 into 10 to the power 10 BQ. Different radionuclides differ greatly in their rates of decay. A common way to characterize this feature is through the notation of half-life. Half-life of a radionuclide denoted by T by 1 by 2 is the time is taken for a sample that has initially say N0 radionuclei is to reduce to N0 2, putting N is equal to N0 by 2 and T is equal to T by 1 by 2 in equation 13.14 we get T by 1 2 is equal to 1 N 2 by lambda is equal to 0.693 by lambda. Clearly, if N0 reduces to half its value in time T 1 by 2, or naught will also reduce to half its value in the same time according to equation 13.16. Another related measure is the average or mean life Tesla. This again can be obtained from equation 13.14. The number of nuclei which decay in the time interval t to t plus delta t is r into t into delta t is equal to lambda and not e to the power minus lambda by t into delta t. Each of them has lived for time t, thus the total life of all these nuclei would be t lambda n naught e minus lambda t. Delta t is the clear, thus some nuclei may live for a short time, while other may live longer. Therefore, to obtain the mean life, we have to sum or integrate this expression over all times from 0 to infinity and divide by the total number of n naught of nuclei at t is equal to 0. Thus, Tesla is equal to lambda n naught integral 0 infinity te minus lambda t dt by n naught is equal to lambda integral 0 infinity te minus lambda t dt. One can show by performing this integral that Tesla is equal to 1 by lambda. We summarize these results with the following: t by 1 by 2 is equal to 1 n 2 by lambda is equal to Tesla 1 n is equal to 2. Radioactive elements, example deuterium, plutonium, which are short-lived, that is have half-lives much less than the age of universe, that is 15 billion years, have obviously decayed long ago and are not found in nature. They can, however, be produced artificially in nuclear reactions. 13.6.2 Alpha decay. A well-known example of alpha decay is the decay of uranium 92U-238 to thorium-90 Ts-234 with the emission of a helium nucleus 2He4. 92U-238 give rise to 90 Th-234 plus 2He4 alpha decay. In alpha decay, the mass of the product nucleus, daughter nucleus, is 4 less than that of the decay nucleus, parent nucleus, while the atomic number decreases by 2 in general alpha decay of a parent nucleus. ZXA result in a daughter nucleus Z2YA4. ZXA gives to Z2YA4 plus 2He4. From Einstein's mass energy equivalence relation, equation 13.6, and energy conservation, it is clear thus this spontaneous decay is possible only when the total masses of the decay product is less than the mass of the initial nucleus. This difference in mass appears as kinetic energy of the product. By referring to a table of nuclear masses, one can check that the total mass of 90 Ts-234 and 2He4 is indeed less than that of 92U-238. The disintegration energy, or the Q value of a nuclear reaction, is the difference between the initial mass energy and the total mass energy of the decay products for alpha decay. Q is equal to mx minus my minus mhe c square. Q is also the net kinetic energy gained in the process, or if the initial nucleus X is at rest. The kinetic energy of the products clearly Q is greater than 0 for exothermic processes such as alpha decay. 13.6.3 Beta decay. In beta decay, a nucleus spontaneously emits an electron. Beta minus decay or a positron beta plus decay. A common example of beta minus decay is 15p32 gives to 16s32 plus E minus plus V dash, and that of beta plus decay is 11Na22 give rise to 10Ne22 plus E plus V. The decays are governed by the equation 13.14 and 13.15, so that one can never predict which nucleus will undergo decay, but one can characterize the decay by a half-life T1/2. For example, T1/2 for the decays above is respectively 14.3D and 2.6Y. The emission of electron in beta minus decay is accompanied by the emission of an antineutron V dash. In beta plus decay, instead a neutrino V is generated. Neutrons are neutral particles with very small, possibly even zero mass compared to electrons. They have only weak interaction with other particles. They are therefore very difficult to detect, since they can penetrate large quantity of matter, even Earth, without any interaction. In both beta minus and beta plus decay, the mass number A remains unchanged. In beta minus decay, the atomic number Z of the nucleus goes up by 1, while in beta plus decay, Z goes down by 1. The basic nuclear processes underlying beta minus decay is conversion of neutron to proton. N give rise to P plus E minus plus V dash, while B plus beta plus decay, it is the conversion of proton into neutron. P give rise to N plus E plus V. Note that while a free neutron decays to proton, the decay of proton to neutron, equation 13.25, is possible only inside the nucleus, since proton has smaller mass than neutron. 13.64 Gamma decay. Like an atom, a nucleus also has a discrete energy level, the ground state and existence states. The scale of energy is, however, very different. Atomic energy level spacings are of the order of eV, while the difference in the nuclear energy level is of the order of MeV. When a nucleus in an existence state spontaneously decays to its ground state or to a lower energy state, a photon is emitted with energy equal to the difference in the two energy levels of the nucleus. This is so-called gamma decay. The energy MeV corresponds to radiation of extremely short wavelength, shorter than the hard X-ray region. Typically, a gamma rays is emitted with a alpha or beta decay, results in a daughter nucleus in an existence state. This then returns to the ground state by a single proton transition or successive transition involving more than one photon. A familiar example is the successive emission of gamma rays of energies 1.17 MeV and 1.33 MeV from the de-excitation of 28Ni60 nuclei formed from beta minus decay of 27CO60. 13.7 Nuclear energy. The curve of binding energy per nucleon EBN given in figure 13.1 has a long flat middle region between A is equal to 30 and A is equal to 170. In this region, the binding energy per nucleon is nearly constant, 8.0 MeV. For the lighter nuclei region, A is less than 30, and for the heavier nuclei region, A is greater than 170. The binding energy per nucleon is less than 8.0 MeV, as we have noted earlier. Now, the greater the binding energy, the less is the total mass of a bounded system, such as a nucleus. Consequently, if nuclei with less total binding energy transform to nuclei with greater binding energy, there will be a net energy release. This is what happens when a heavy nucleus decays into two or more intermediate mass fragments, fusion, or when light nuclei fuse into a heavier nucleus, fusion. Exothermic chemical reaction underlie conventional energy sources such as coal or petroleum. Here the energies involved are in the range of electron volts. On the other hand, in a nuclear reaction, the energy release is of the order of MeV. Thus, for the same quantity of matter, nuclear sources produce 1,000,000 times or more energy than a chemical source. Fusion of 1 kg of uranium, for example, generates 10 to the power 14 J of energy. Compare it with burning of 1 kg of coal, that gives 10 to the power 7 joule. 13.7.1 Fission. New possibilities emerge when we go beyond natural radioactive decays and study nuclear reactions by bombarding nuclei with other nuclear particles such as proton, neutron, alpha particles, etc. A most important neutron-induced nuclear reaction is fusion. An example of fusion is when a uranium isotope 235U92 bombarded with a neutron breaks into two intermediate mass nuclear fragments. 0N1 plus 92U235 give rise to 92U236 give rise to 56Ba144 plus 36Kr89 plus 30N1. The same reaction can produce other pairs of intermediate mass fragments. 0N1 plus 92U235 give rise to 92U236 give rise to 51Sb133 plus 41Nb99 plus 40N1, or as other example, 0N1 plus 92U235 give rise to 54Xe140 plus 38Sr94 plus 20N1. The fragments produced are radioactive nuclei. They emit beta particles in succession to achieve stable end products. The energy release, the Q value in the fusion reaction of nuclei like uranium, is of the order of 200 MeV per fusioning nucleus. This is estimated as follows. Let us take a nucleus with A is equal to 240 breaking into two fragments each of A is equal to 120. Then EBN for A is equal to 240 nucleus is about 7.6 MeV. EBN for the 2A 120 fragments nuclei is about 8.5 MeV. Therefore, gain in binding energy for nucleon is about 0.9 MeV. Hence, the total gain in binding energy is 240 into 0.9 or 216 MeV. The disintegration energy in fusion events first appears as the kinetic energy of the fragments and neutrons. Eventually, it is transformed to the surrounding matter, appearing as heat. The source of energy in nuclear reactors which produce electricity is nuclear fusion. The enormous energy released in an atom bomb comes from uncontrolled nuclear fusion. We discuss some details in the next session how a nuclear reactor functions. 13.7.2 Nuclear reactor. Notice one fact of great importance in the fusion reactions gives in equation 13.26 to 13.28. There is a release of extra neutrons in the fusion process. Averagely, 2 1/2 neutrons are released per fusion of uranium nucleus. It is a fraction since in some fusion events 2 neutrons are produced in some 3, etc. The extra neutrons in turn can initiate fusion processes proceeding still more neutrons and so on. This leads to the possibility of a chain reaction as was first suggested by Enrico Fermi. If the chain reaction is controlled suitably, we can get a steady energy output. This is what happens in a nuclear reactor. If the chain reaction is uncontrolled, it leads to explosive energy output. As in a nuclear bomb, there is, however, a hurdle in sustaining a chain reaction. As described here, it is known experimentally that slow neutrons, thermal neutrons, are much more likely to cause fusion in 92U235 than fast neutrons. Also, fast neutrons liberated in fusion would escape instead of causing another fusion reaction. The average energy of neutron produced in fusion of 92U235 is 2 MeV. These neutrons, unless shot down, will escape from the reactor without interacting with the uranium nuclei unless a very large amount of fissile material is used for sustaining the chain reaction. What one needs to do is to slow down the fast neutrons by elastic scattering with light nuclei. In fact, Chadwick experiment showed that in an elastic collision with hydrogen, the neutron almost comes to reset and proton carries away the energy. This is the same situation as when a marble hits head-on an identical marble at rest. Therefore, in reactors, light nuclei called moderators are provided along with the fissionable nuclei for slowing down fast neutrons. The moderators commonly used are water, heavy water, D2O, and graphite. The Apsara reactor at the Bhabha Atomic Research Center, BARC, Mumbai, use water as moderator. The other Indian reactors which are used for power production use heavy water as moderator. Because of the use of moderator, it is possible that the ratio K of the number of fusion produced by a given generation of neutrons to the number of fusion of the preceding generation may be greater than 1. This ratio is called the multiplication factor. It is the measure of the growth of rate of neutrons in the reactor. For K is equal to 1, the operation of the reactor is said to be critical, which is what we wish it to be for steady power operation. If K becomes greater than 1, the reaction rate and the reactor power increases exponentially. Unless the factor K is brought down very close to unity, the reactor will become supercritical and can even explode. The explosion of the Chernobyl reactor in Ukraine in 1986 is sad reminder that accidents in a nuclear reactor can be catastrophic. A reaction rate is controlled through control rods made out of neutron absorbing materials such as cadmium. In addition to control rods, reactors are provided with safety rods which, when required, can be inserted into the reactor and K can be reduced rapidly to less than unity. The more abundant isotope 92U-238 in naturally occurring uranium is non-fissionable. When it captures a neutron, it produces the highly radioactive plutonium through these reactions. 92U-238 plus N gives to 92U-239U give rise to 93Np-239 plus E minus plus V dash. 93Np-239 give rise to 94Pu-239 plus E minus plus V dash. Plutonium undergoes fusion with slow neutrons. Figure 13.5 shows the schematic diagram of a nuclear reactor based on thermal neutron fusion. The core of the reactor is the site of nuclear fusion. It contains the fuel elements in suitable fabricated form. The fuel may be, say, enriched uranium, that is, one that has greater abundance of 92-235 uranium than naturally occurring uranium. The core contains a moderator to slow down the neutrons. The core is surrounded by a reflector to reduce leakage. The energy heat released in fusion is continuously removed by a suitable coolant. A contaminant vessel prevents the escape of radioactive fusion products. The whole assembly is shielded to check harmful radiation from coming out. The reactor can be shut down by means of rods made of, for example, cadmium that have high absorption of neutrons. The coolant transfers heat to a working fluid which in turn may produce steam. The steam drives turbines and generate electricity. Like any power reactors, nuclear reactors generate considerable waste products. But nuclear wastes need special care for treatment since they are radioactive and hazardous. Elaborate safety measures both for reactor operation as well as handling and reprocessing the spent fuel are required. These safety measures are distinguishing features of the Indian Atomic Energy Program. An appropriate plan is being evolved to study the possibility of converting radioactive waste into less active and short-lived material. 13.7.3 Nuclear fusion. Energy generation in stars. When two light nuclei fuse to form a large nucleus, energy is released since the larger nucleus is more tightly bound. As seen from the binding energy curve in figure 13.1, some example of such energies liberating nuclear fusion reactions are 1H1 plus 1H1 give rise to 1H2 plus E plus V plus 0.42 MeV plus 1H2 plus 1H2 give rise to 2He3 plus N plus 3.27 MeV. 1H2 plus 1H2 give rise to 1H3 plus 1H1 plus 4.03 MeV. In the first reaction, two protons combine to form a deuteron and a positron with a release of 0.42 MeV energy. In reaction 13.29b, two deuterons combine to form a light isotope or helium. In reaction 13.29c, two deuterons combine to form a triton and a proton. For fusion to take place, the two nuclei most common close enough so that the attractive short-range nuclear force is able to affect them. However, since they are both positively charged particles, they experience Coulomb repulsion. They therefore must have enough energy to overcome this Coulomb barrier. The height of the barrier depends on the charge and radii of the two interacting nuclei. It can be shown, for example, that the barrier height of two protons is 400 Kelvin V and is higher for nuclei with higher charges. We can estimate the temperature at which the two protons in a proton gas would averagely have enough energy to overcome the Coulomb's barrier. 3 by 2 kT is equal to K is equivalent to 400 keV, which gives T is equivalent to 3 into 10 to the power 9 K.
When fusion is achieved by raising the temperature of the system so that particles have enough kinetic energy to overcome the Coulomb's repulsive behavior, it is called the thermonuclear fusion. Thermonuclear fusion is the source of energy output in the interior of stars. The interior of the Sun has a temperature of 1.5 into 10 to the power 7 Kelvin, which is considerably less than the estimated temperature required for fusion of particles of average energy. Clearly, fusion in the Sun involves protons whose energies are much above the average energy. The fusion reaction in the Sun is a multi-step process in which the hydrogen is burned into helium. Thus, the fuel in the Sun is the hydrogen in its core. The proton-proton pp cycle by which this occurs is represented by the following sets of reactions. 1H1 plus 1H1 give rise to 1H2 plus E plus V plus 0.42 MeV. E plus E minus alpha plus 1.02 MeV. 1H2 plus 1H1 give rise to 2He3 plus alpha plus 5.49 MeV. 2He3 plus 2He3 give rise to 2He4 plus 1H1 plus 1H1 plus 12.86 MeV. For the fourth reaction to occur, the first three reactions must occur twice, in which case two light helium nuclei unite to form ordinary helium nucleus. If we consider the combination 2 1 plus 2 2 plus 2 3 plus 4, the net effect is 4 1 H1 plus 2E minus give rise to 2He4 plus 2V plus 6 alpha plus 26.7 MeV, or 4H plus 4E minus give rise to 2He4 plus 2E minus plus 2V plus 6 alpha plus 26.7 MeV. Thus, 4 hydrogen atom combine to form an 2He4 atom with a release of 26.7 MeV of energy. Helium is not the only element that can be synthesized in the interior of star. As the hydrogen in the core gets depleted and becomes helium, the core starts to cool. The star begins to collapse under its own gravity, which increases the temperature of the core. If the temperature increases to about 10 to the power 8 Kelvin, fusion takes place again, this time of helium nuclei into carbon. This kind of process can generate through fusion higher and higher mass number elements, but elements more massive than those near the peak of the building energy curve in figure 13.1 cannot be so produced. The age of the Sun is about 5 into 10 to the power 9 Y, and it is estimated that there is enough hydrogen in the Sun to keep it going for another 5 billion years. After that, the hydrogen burning will stop and the Sun will begin to cool and will start to collapse under gravity.
which will raise the core temperature. The outer envelope of the sun will expand, turning it into the so-called red giant. 13.7.4 Controlled thermonuclear fusion. The natural thermonuclear fusion process in a star is replicated in a thermonuclear fusion device. In controlled fusion reactors, the aim is to generate steady power by heating the nuclear fuel to a temperature in the range of 10 to the power 8 Kelvin. At this temperature, the fuel is a mixture of positive ions and electrons plasma. The challenge is to confine this plasma, since no container can stand such a high temperature. Several countries around the world, including India, are developing techniques in these connections. If successful, fusion reactors will hopefully supply almost unlimited power to humanity.
Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.